Hello audience, welcome to this lecture on convergence of Fourier series and Fourier transform of the standard signals. The learning outcomes of this session are, at the end of this session you should be able to analyze the convergence of the Fourier transform, compute the Fourier transform of the standard signals, and solve the problems using Fourier transform. We are going to review the Fourier transform formula. The Fourier transform can be represented either as capital X of omega or capital X of f, and the formula for the Fourier transform capital X of omega is integral minus infinity to infinity x of t e power minus j omega t dt. And if we use the Fourier transform in the frequency domain, which is capital X of f, the capital X of f is equal to integral minus infinity to infinity x of t e power minus j 2 pi f t dt. So I simply replaced omega is equal to 2 pi f, that's all. The inverse Fourier transform can also be written using the two equations. X of t is 1 by 2 pi integral capital X of omega e power plus j omega t d omega, and which is also equal to the integral capital X of f e power plus j omega. In that place you are getting e power j 2 pi f t df. So here in the place of omega you are getting 2 pi f for the second equation. Again, if you are going to substitute here in the place of d omega, if you substitute simply omega is 2 pi f, the 2 pi and the 2 pi will get cancelled. That's why in the second integral for the inverse Fourier transform using the variable f, there is no 1 by 2 pi here. Now we are going to discuss what is the convergence of Fourier transform and also what are the conditions. Now the convergence of the Fourier transform means the Fourier transform, the integral, it should converge to a value less than infinity. Now for that there are certain conditions which the signal should satisfy, and those conditions they are called Dirichlet conditions. Now these Dirichlet conditions they even apply for the application of a Fourier series as well. So the convergence of the Fourier transform or the convergence of the Fourier series, the conditions which the signal must satisfy, they are called Dirichlet conditions. Now the first condition is the signal must be absolutely integrable. So if you take the integral of mod x of t dt, that integral should be less than infinity. That's why it is called absolutely integrable, because we are taking the absolute value or the mod value of x of t and then we are integrating it, and the integral should be less than infinity. Therefore this condition is called the signal must be absolutely integrable. Now the second condition is that the signal x of t must have only finite number of maxima and minima. And the third condition is the signal x of t should have finite number of discontinuities. Now these three conditions they are called Dirichlet conditions. Now these are the conditions that are going to be satisfied by the signal x of t, then we can apply either Fourier transform or Fourier series. Now we are going to review some standard signals before we compute the Fourier transform of the standard signals. Now here we are seeing a unit step signal u of t, which is 1 for t greater than 0. Then here we are seeing a rectangular pulse. The rectangular pulse is simply 1 in a rectangular region between minus 0.5 to 0.5. Then there is the triangular signal, and then there is also the sync signal. The sync signal is simply sine pi t by pi t. Now since the t is in the denominator, we are going to have this sine wave which will continuously decrease in amplitude, As the time increases, the amplitude will decrease because t is in the denominator. Now here we are also going to discuss another important signal, which is called signal or signum function, which is having this particular shape. So the signum function is positive 1 for all t greater than 0, and it is negative 1 for all negative values of time. Now, by looking at the waveform of this signum function, we can see the signum function is, of course, having the shape of u of t on the positive side. So, of course, we will have u of t. Now, if you see on the negative side, it is not just u of minus t, and it is also having a negative, which is a negative amplitude, which is -1. So we have to put u of t minus u of minus t. So this u of t is going for this positive values of 1 on t greater than 0, and here on the negative time side there is a -1 here. For that we are putting minus of u of minus t. Now the first problem which we are going to solve is computing the Fourier transform of the unit step signal u of t. Now the unit step signal can be obtained by the integration of the impulse signal, which is delta of t. So we can write u of t is the integral of delta tau d tau. Now from the integration property we know the integration of x of tau d tau. If we take the Fourier transform of that integral of x, then we are going to get capital X of f by j2 pi f plus delta f into capital X of 0 by 2. Now we know the Fourier transform of this delta of t, which is x of t, in our case is simply 1. Therefore capital X of f, which is the Fourier transform of delta of t, is 1. Now hence we can substitute in the place of capital X of f here 1, and hence even x of 0 also will be 1, and we are going to get the Fourier transform of u of t, which is the integral of delta tau d tau, as capital X of f, which is 1 divided by j 2 pi f plus delta f into x of 0. X of 0 is also 1 divided by 2. So therefore the Fourier transform of u of t is simply 1 by j 2 pi f plus delta f by 2. Now we are going to compute the Fourier transform of the signum function. Now the signum function can be written as we saw in the previous slides, u of t minus u of minus t. Now we know already from the previous problem u of t Fourier transform is 1 by j2 pi f plus delta f by 2. Now we are going to apply the time reversal property to get Fourier transform of this u of minus t, which will be simply replace wherever f is there with minus f. So we are going to get the Fourier transform of u of minus t as 1 divided by minus j2 pi f plus delta of minus f by 2. Now we can combine both these equations and we can get the Fourier transform of signum function very simply as the Fourier transform of signum function is simply Fourier transform of u of t minus Fourier transform of u of minus t from this formula. And the Fourier transform of u of t is already computed here. Therefore, the Fourier transform of the first part is the Fourier transform of u of t, which is 1 by j2 pi f plus delta f by 2, then minus the Fourier transform of u of minus t, which is computed here, which is 1 by minus j2 pi f plus delta of minus f by 2. Now the first two terms they are going to add. You will get 2 by j2 pi f plus delta f by 2 minus delta minus f by 2. Now delta f is equal to delta of minus f because delta f is an even function. So these two will get cancel each other, and the Fourier transform of the signum function will be simply 1 by j2 pi f. Next, we are going to compute the Fourier transform of the exponential signal e power minus at ut. Now, the Fourier transform can be written as the integral e power minus at ut into e power minus j 2 pi ft dt. Now we can combine e power a into e power b as e power a plus b. So we are going to get this integral e power minus a plus j 2 pi ft dt. And also, since u of t is there, the lower limit will change from minus infinity to 0, because u of t starts at 0. T is greater than or equal to 0, then only u of t will have the value of 1. Therefore the lower limit is changing from minus infinity to 0. Now we have to simply calculate the integral of e power minus a plus j 2 pi ft, which is simply e power minus a plus j 2 pi f into t divided by that factor, which is minus a plus j 2 pi f. Now we have to substitute the limits infinity and 0. So we are going to get the first limit as e power minus infinity, which will be 0. And if you apply the lower limit, which is 0, you will get e power 0. E power 0 will be 1. So the final answer will be 1 by a plus j 2 pi f. Therefore, the Fourier transform of e power minus at into u of t is simply 1 by a plus j 2 pi f. Now we are going to compute another similar Fourier transform, which is the Fourier transform of the signal x of t e power minus a mod t into u of t. Now we are going to first define what is the mod t. Now mod of t is t when t is positive or t greater than or equal to 0, and mod of t will be minus t when t is less than 0. Now this signal, given signal is e power minus a mod t multiplied by u of t, and we know that u of t is only non-zero for t greater than or equal to 0. So in that condition, mod t when t greater than or equal to 0 will be only t. Therefore the given signal x of t reduces to e power minus at ut, because u of t is only present for t greater than or equal to 0. There the mod t becomes t. So e power minus a mod t ut, it actually reduces to simply e power minus a t ut. Then we have to compute the Fourier transform of the signal e power minus at mod t, which is again previously calculated in the previous slide as 1 divided by a plus j 2 pi f. Next, we are going to compute the Fourier transform of e power at into u of minus t. Now, this is a non-causal signal because the signal is having the time reversed unit step signal u of minus t. So, this is a non-causal signal. Now, let us take here e power minus at ut as x of t, the signal which we computed in the previous slides. Now we know the Fourier transform of that signal e power minus at ut is simply 1 by a plus j 2 pi f, and then we substitute here t with minus t on both sides. Then you are going to get, in the place of e power minus at, e power plus at, and in the place of u of t you will get u of minus t, which is simply x of minus t. Now we already know by the time reversal property, x of minus t will have the Fourier transform capital X of minus f. So wherever the f is there, we have to substitute minus f. Therefore, the Fourier transform of the signal e power at u of minus t will be simply 1 divided by a plus j 2 pi into, wherever you have f, you have to put minus f. So we'll have a minus f. Therefore, the Fourier transform of the signal e power at u of minus t will be 1 divided by a minus j 2 pi f. Thank you, audience, for your patient hearing. Thank you very much.